I welcome you all to this course Fundamentals of Compressible Flow. Now, we are in the first module 1, which is essentially contains the topics review of concepts of fluid mechanics and thermodynamics. So, essentially at UG level entire portion of this fluid mechanics and thermodynamic courses has been covered, but however, since it is an advanced course on compressible flow, it is now a customary to revisit the contents of some of the important contents that we are going to use in this course. Now, in this lecture we will concentrate on three important aspects. First is concept and definition of fluids, second is properties of fluids, and third is classifications of fluid flow. So, essentially this course is about fluids, so which contains mostly liquids and gases, and our main focus would be on mostly on gases. So, based on that we are going to discuss about the properties that are mostly important for the gases. The next part is the first part, or what we say is the concept and definition of fluids, but before you go for those definition of fluids, it is the most important concept of matter that exists in three different states. So, that is namely solid, liquid and gas. So, the substances that are in liquid and gas phase, they have a common characteristics and they are called as fluids. But however, there is a essentially catch between the catch for the solids and liquids, and we have a very fundamental scientific definitions for it. So, which means the which is the essentially the ability of any substance to resist the shear. To start these things, let me explain the way we define the scientifically the definition of a solid. So, we can imagine a solid block is being placed on a surface, and in a similar way we can also see there is a container having a liquid and same container or similar container with gases in it. So, these gases are spread all around the container, above or within it. So, what the basic philosophy of solid, and this we say solid and this we say liquid and this we say gases. So, when you actually see the scientific definition for this, what has been done is that all these substances, they have their own weights, and because of their own weights a typical solid blocks is inherently a kind of a compression at some point, some location, which we say this, and its weight is always acting downwards. Because of this, we any point on this solid block is inherently experiences a kind of stress or a kind of load onto it. And in fact, this when you actually put at this cross section for this, when you put this, then typically it looks in the manner that same point, if you take any cross section like this A or A dash, A double dash, and this is at an angle theta to the horizontal, then what we see is for solids that this solid block is a kind of a compressive load and a shearing load at that surface, and all other side surfaces it experiences, there is no force, and from the bottom this there is a compressive load, and that is nothing but the pressure acting from the bottom surface. So, this is what we see at any locations A or any location at the cross section location at point A, and making a cross section A dash and A double dash. In a similar philosophy or similar equations, if you can draw the similar story here, then what we see for these liquids and gases, it is something like a structure in which all the surfaces except the inclined surfaces, they experience a pressure which acts on this fluid element at that locations. But in this inclined location, what you see, I will say B dash, B double dash. So, this turns out to be a, so here instead of stress we experience a pressure, and but we have a shear stress which is 0 in this case, since the liquid and gases they are at rest. So, this is the basically scientific definition that tells a basic distinction between solid and fluid on the basis of substances ability to resist the applied shear. Next is the solid can resist the applied shear by deforming, whereas the fluid deforms continuously under the influence of shear stress, no matter how it is small. The fluid is also defined as a substance that deforms continuously when acted upon a shear stress or shear force of any magnitude. Now, when, as I told earlier, when the fluid is at rest, there is no shearing force and all the forces are perpendicular to the plane to which in which it is present. Now, for solids the stress is directly proportional to strain, and for fluids the stress is proportional to the strain rate. So, typically we say sigma, which is directly proportional to strain, that is for solids, and for fluids this stress is proportional to another factor which is called as strain rate, and then down the line we will say this strain rate as du by dy. We will define this is termed as strain rate. When a constant stress is applied, the solid eventually deforms and deforms at a fixed strain angle, whereas fluid never stops deforming and approaches a certain strain. The next fundamental definition that goes is that after having the definition between solid and fluid, then we will talk about only on fluids that essentially constitutes liquids and gases. So, as we say the as we know that liquids and gases they resemble a common behavior, however, there are some distinctions. So, which we can characterize under certain conditions. So, first fundamental difference is that it is easy to compress a gas, whereas liquids are inherently treated as incompressible. A given mass of liquid occupies a fixed volume and irrespective of size and shape of the container, whereas gases have no fixed volume and they expand continuously unless restrained by the vessel. So, as it is known that liquids contains a free surface, whereas the gases occupies the entire volume of the vessel. And but our main focus in this course will be mostly on gases, because these gases are compressible in nature. Now, moving back to the the next part of this lecture, which is properties of the fluids. So, the thermodynamic definition of the property of a fluid means it is a characteristics of the systems that depends on the state of a system. So, these properties may be intensive, which is mass independent, or extensive, which that depends on the size of the system. So, a classical example for this type of intensive and extensive properties is given. For example, if you have a kind of a container and it has certain mass, it contains certain mass of any gas, and it has a volume V, and it inside this the properties are defined by pressure, temperature and density. So, for example, if you make these things equally half, so then what is going to change in this process? So, your M becomes half, volume becomes half, but pressure, temperature, density do not change. So, which says that this mass and volume they are extensive properties, pressure, temperature and density they are treated as intensive properties. So, likewise this will apply for any kind of properties for which we can make this kind of distinctions. Now, in this category of properties of fluids, we will talk about the following properties, that is thermodynamic properties and equation of state typically for gases, kinematic properties, transport properties and some other miscellaneous properties which we already know. Now, about these properties, while exaggerating more onto this, we will talk about the thermodynamic properties, sometimes we will talk about the fluid properties as and when they appear. And most of these things already, although it is known, but it is advised that these properties we are going to use routinely at any subsequent lectures down the line. So, that is the reason this properties needs attention at this stage. So, the thermodynamic properties, that is the mostly when you talk about the fluids there or gases, they are essentially treated as a pure substances, and most of the properties are related to the thermodynamic properties. And at the same time, when you look at fluid mechanics angles to the flow, the velocity is one of the parameter which is treated as a fluid properties. But when a flow interacts during a situation when the flow moves or flow interacts or flow passes to a medium, there are change in the properties and it interacts with other fluids. As and when it does, it changes its properties, and it mainly pressure, which we mainly consider as a pressure, temperature and density. The first important or fundamental property, that temperature, it comes from the zeroth law of thermodynamics. So, apart from this, the pressure and densities that are independent properties of any given substances. So, this is all about when you do about this the three important properties, pressure, temperature, density or specific volume. But in fluid mechanics aspects, when you deal with fluid statics, since when you multiply this density with the acceleration due to gravity, we call this another term, we come across another term which is known as specific weight, and that is the weight of the fluid per unit volume. There is another property, specific gravity, which is defined as the ratio of density of any arbitrary fluid to the standard reference fluids. And in our situations, we say that the standard reference fluids, if it is a liquid, it is water, and if it is a gas, it is air. Now, we move to the basic thermodynamic properties. So, when we talk about the thermodynamic properties, we essentially talk about the first law or laws of thermodynamics. So, in the first law, which is essentially the concept of conservation of energy, it introduces a properties which is known as internal energy for a static fluid, and or in this case we call it as a closed system or fixed mass system, and this internal property is essentially a function of temperatures. Now, in case of open systems, and the thermodynamic definition of an open system is that where both mass and energy interactions are possible. So, in this particular open system, the properties that is of importance is enthalpy, and its basic definition is internal energy plus U plus P by rho, and many times this P by rho is termed as P pressure times specific volume, or you call this as a flow work. So, the open systems gives a characteristics which is called as enthalpy, and in having defining these two terms, we again call the total energy of the systems E, and it is essentially composed of three parameters: internal energy, kinetic energy, that is V square by 2, and potential energy G z, and this definition is made for unit mass basis. Then moving further, we will go to the second law of thermodynamics, and this second law of thermodynamics introduces the term entropy, and in fact it gives the directionality of a particular systems, whether a flow should occur in certain direction or not. So, increase of entropy will essentially drive the flow in certain directions, and this definition of entropy comes from the fact that when there is a heat interactions and the entropy change in for a system is defined by ds is equal to delta q by T, that is change of heat divided by the temperature in which this change is occurring. So, if you look at this kind of equations, the first part of equation, this comes from the first law, entropy part that comes from the second law, and based on the first law and second law combined, we get these two equations, which is known as Gibbs equation, and many a times we call this as a TdS relation. So, in fact, one can derive these equations by combining first law and second law. Now, to do that, let us talk about, let us write what is this dq from this definition as TdS. We also know that rate of work transfer per unit mass basis, we can say P dV. Now, if you recall the first law, which is dq minus delta q minus delta w is equal to change in the internal energy, and by putting these equations, what you say, TdS minus PdV and so this is nothing but the first TdS relations, and by putting H is equal to or internal energy equal to H minus pressure times specific volume, since density is the inverse of specific volume. So, from the first TdS relations, when you put u as this, so what we can write is TdS is equal to dH minus P times V plus P dV. So, this can be expanded as dH minus P dV minus V dP plus P dV. So, these two terms gets cancelled. Ultimately, we get the second TdS relation as dDs is equal to dH minus V dP. So, these two relations are very essential when we deal with the compressible flow analysis. Moving further, we will now talk about the equation of state or thermodynamic relations for gases, and this is essentially governed as it is known thermodynamically that all the gases at high temperature and low pressures, they are in agreement of perfect gas law, which is P is equal to rho R T, where and R is nothing but the characteristics gas constant, and R bar is nothing but universal gas constant. And they are related through the parameter known as molecular weight. In fact, for our analysis, we will routinely use this expression, which is known as equation of state. Now, apart from this, we also are of another parameter which is of more interest, which is specific heat, and this is related to the temperatures, because essentially temperature is the main cause of heat transfer to take place. So, a specific heat is defined as the amount of energy required per unit mass of fluid for the unit rise of temperature. Typically liquids, we do not talk about liquids because they have a single specific heat, whereas for the gases they can have two different types of specific heats, because as you know the gases follow the law P is equal to rho R T. So, the change can occur at for a given temperature difference, we can have change or amount of heat required. We can do it by maintaining a constant pressure or maintaining a constant volume. So, accordingly we say it is a specific heat at constant pressure Cp, other one is the specific heat at constant volume, and based on the first law of thermodynamics they have been related with enthalpy and entropy, that is Cp is related to enthalpy and Cv is related to internal energy. So, the difference between the Cp and Cp is nothing but the characteristics gas constants. In addition, we have another parameter called as specific heat ratio gamma, and based on this definition the Cp can be related with the parameters gamma is equal to Cp is equal to gamma r by gamma minus 1, whereas Cb is equal to r by gamma minus 1. It is to be remembered that these two expressions we will be frequently using for the when you deal with the main compressible flow. Now, we will come back again for the kinematic properties, which is essentially fluid properties. In general, when the fluid is in motion, it is essentially defined through a velocity vector in a particular time and space systems, or it is called as a field. So, this velocity is a vector function of position and time, which is represented as v vector as a u plus v plus w, and they are all of them are functions of x, y, z and t, that is in the Cartesian coordinates, and these position vectors can be found out by integrating this velocity vector with time, and so this is what we call as a position vector. Acceleration can also be found out by differentiating the velocity vector, and there is another term which we call as angular velocity. This angular velocity is nothing but the mathematical interpretation of curl of velocity vectors. The other parameter of interest, we also define the volume flow rate dV by dt, and also we define volume expansion rate. How the volume changes with respect to time, and this is nothing but the dot product of velocity vector, that is gradient of velocity vectors. The next important properties which is are of more interest for the fluids, we call this as a first property is vapor pressure, and this is mainly concentrated when your fluid is a liquid. And so, normally the liquid evaporates when it is kept in a container and open to the atmospheres. So, it is very likely that since it has a free surfaces and these free surfaces have a least energy and they try to evaporate from the surface. So, the vapor, so when the vapor is at saturated state, this that particular state we call this as a vapor pressures. And in a fluid motion, if the pressure at some location is lower than that of vapor pressure, a kind of bubbles start forming, we call this as a cavitation. The other properties of importance is surface tensions, which is essentially the properties when these liquids and gases come in contact together, and this is governed by the molecular interactions and typically known as surface tensions. However, in our philosophy we will not be going to use this property exhaustively. And in fact, now we are coming to another important properties, which is bulk modulus, and it is the property of a fluid that represents the variation of density change with respect to pressure at constant temperatures. Ideally, if you look at the equation of state, P is equal to rho R T. So, we can say that the pressure can change with respect to density. The pressure can change with respect to density by keeping temperature as constant. So, we define a parameter called as a bulk modulus EV. This is what we say rho times dP by d rho at constant temperatures. Another parameter of interest is coefficient of thermal expansion, which we say as beta. How the volume, specific volume changes with the temperature. So, beta is 1 by V dV by dt. Now, in fact, from the equation of state one can derive that beta turns out to be 1 by T if from the equation of states. Now, from this equation we can write rho is equal to P by R T. Now, one can find out d rho by dt at constant pressure, which as P by R into minus 1 by T square. So, if you take this P by R as rho times T, so dP by dt reduces to minus P by R T into 1 by T. So, finally, from this expression we can, and this is nothing but P by R T is nothing but rho. So, after simplifications we get this term beta to be inverse of temperature, absolute temperature for an ideal gas. The next important properties, which is called as speed of sound. So, so this parameter we will be looking at in more exhaustive form in the subsequent class. Just for the sake of continuity, I am just explaining that the one of the important consequence of compressibility of gas is the fact that when a gas moves in a medium, it creates a pressure disturbance, and this pressure disturbance moves at certain speed, which is known as the speed of sound, or typically known as acoustic speed. This acoustic speed is defined by C is equal to dP by d rho. This is the fundamental definition of acoustic speed. Now, if the medium is treated to be isothermal, this expression reduces to this dP by d rho at becomes RT if it is an isothermal case. In such situations, speed of sound becomes square root of RT. The now if, but that is a very unlikely event, but the most importantly when the speed of sound is approximated by keeping the medium to be isentropic, for which this dP by d rho is calculated, and that is comes out to be square root of gamma RT for an ideal gas. So, the point that I need to emphasize here is that although we call this as a speed of sound, but its very basic definition talks about the parameters which are essentially the properties. So, even though it is a speed, but it is a property because it contains the terms gamma R T for a given situation or for a given gas. There are very other properties of some other properties, we call them as a transport properties, that is the friction and heat conduction effects becomes sometimes significant when the velocity interacts with these parameters. In such a situation, when the fluid is in motion, these properties affects the flow parameters. So, during such situation we define some properties which is viscosity that relates momentum flux to the velocity gradient, thermal conductivity that relates heat flux to the temperature gradient, diffusion coefficient that relates mass transport to the concentration gradient. So, the first properties is the viscosity, it relates the momentum flux to the velocity gradients. So, essentially the viscosity is the term which is defined as the ability of a fluid to flow freely. A classical definition goes in this way, that the viscosity is the property of a fluid that relates applied stress to the resulting strain rate. So, based on that we define a term which is called as a shear stress, and that relates the strain rate which is du by dy and one can find out this dy by dy as the V by h. So, a classical example typically is given when there is a fixed plate and there is a moving plate, and in the moving plate a force is given, and in between the moving plate and fixed plate there is a viscous fluid. When this plate is given to a certain by velocity v, and the fluid layers gets sheared. So, at one instance at time t is equal to 0, at time t is equal to t1 and time t is equal to t2, the plate position, upper plate position is at these locations. So, based on that, if you talk about the velocity profile, it says that the top layer of the fluid undergoes maximum change, whereas velocity at the fixed one it is almost 0. So, the velocity changes from 0 to its final value within this distance h, which is the separation distance between the top plate and bottom plate. The other properties of importance, which is the, now when we actually calculate the viscosity for the gases, it is seen that for gases the viscosity increases with the temperatures. So, many a times when we deal with very high temperature flow gases, we need to find out how viscosity changes with the temperatures. So, for that we typically refer a classical law which is called as Sutherland's law, and which essentially relates the viscosity of gases at any arbitrary temperature T, that is mu has to be defined at any arbitrary temperature T, provided we know the viscosity value at the given temperatures. And this is related by this expression where S is known as Sutherland's constant. Similarly, we move on to properties called thermal conductivity, and in fact, in our mostly in our situations the gases have least thermal conductivity, and it does not exhibit a very sensitive behavior as it does with respect to solids. But however, one can evaluate this change in the thermal conductivity with respect to temperature, which is almost similar to that of a Sutherland's law. The other parameter of interest is the diffusion coefficients. Once again, this diffusion coefficient is a parameter that talks about when there are two gases, you have to find out how one gas diffuses into the other. So, this is something like so for that we define two fundamental concept. We call this as a self, either it can have a self diffusion, that is a same gas diffuses into other, that is for example, one gas is moving very high velocity and same gas is moving at one other velocity. When they mix together, that means one gas gets penetrating into the other, then we call this as a for such set of situation as a self diffusion. But similar thing, if the gases are treated as a two different entities, that means one gas tries to diffuse into other, then we call this as a binary diffusions. And in fact, more and more we can have the concept of multi diffusion, that means more and more species gets diffused into other. But that is not of our interest. But however, one particular interest we want to say that when you deal with the high speed flow of gases, then when one gas tries to diffuse into other, then we call this as a coefficient called as a binary diffusion coefficients, which is calculated by these expressions D12, and it is empirical relations. Of course, we do not need to remember, but just to say that one, that is just the way of evaluating a diffusion coefficients that talks about how a diffusion, how a gas diffuses into other. So, in these expressions there are parameters which is of interest, is that we want to find out the diffusion process occurring at certain pressure P. Other parameters of interest, since we have two species, we have two molecular weights M1 and M2, and this pressure also happening at, we want to find out diffusion process at certain pressure, temperature and certain pressures. Apart from this, there are other parameter of interest which you know, which you should know, is that what is the temperature of species 1 or what is the temperature of species 2. These are absolute temperatures, and apart from that we also need to know a parameter which is called as collision, effective collision parameter. This effective collision parameter, which is sigma 1 2, which is equal to sigma 1 plus sigma 2 by 2, and in fact sigma 1 is nothing but the molecular diameter of 1 and sigma 2 the for the second gas. Now, after having defining all these things, so if you just read out something about fluid statics, if the, that means if the gas is not moving at all, so we treat this them as a fluid statics. Under that behavior, we commonly refer these hydrostatic equations, and the law that governs these things is known as Pascal's law, and the equation of hydrostatic equation, which is fundamental definition, is Z1 minus Z2, normally Z is equal to P2 minus P1 by rho g. So, but the very basic definition in our analysis, whenever you will be using this, whenever there is a the term the potential energy which is associated with the flow, this parameter makes of importance. In fact, it is a very fundamental aspects when you start the fluid mechanics course or fluid statics. And the last segment of this lecture is the classifications of the fluid flow. Essentially all these things are been covered as a the fundamentals in the UG level. So, first is whether the flow is viscous or inviscid. So, viscous or inviscid means that during the flow, whether the role of viscosity, whether there is a role of viscosity that is affecting the nature of the motion. Other way is that flow is completely inviscid. So, that means in which the for viscous flow frictional effects becomes predominant, and also we need to take into parameter viscosity of the gas taken into account. And in our day to day life, we typically call potential flows are inviscid nature of flow, and the boundary layer flow as typically governed through this viscous flow. The next category of the flow is internal flow or external flow. So, whether a flow occurring in an medium which is completely enclosed, for example, the flow through a pipe, a gas is moving in a pipe through certain pressure difference or a duct. So, these particular things we call this as internal flow, and if the flow does not have any bounded surface, for example, flow over an aircraft, there is no bounded surface. So, this is treated as a external flow. Here our main focus comes into it, which is incompressible and compressible flow. So, essentially in our entire domain we will be mainly looking at the flow nature which is compressible. So, under what circumstances we say the flow to be compressible? Whenever there is a flow occurring in a system or in a duct system, and at two arbitrary locations, if you try to evaluate density and try to see if there is a change in the density more than 5%, such a case we call this to be compressible. So, we will talk more about this when we actually deal with the situations why the density is going to change. But in the other extreme of this flow, which is incompressible, typically it is meant for liquids. But one point I need to emphasize here, that when you talk about gases, these gases under certain conditions they behave in two manner, whether they exhibit the nature of incompressibility or they exhibit the nature of the compressibility is the question mark. That is essentially decided under what pressure difference this flow is occurring. Other type of flows, that is steady flow and unsteady flow. So, when you say steady flow, we essentially see how the parameter is any fluid parameter which is changing with time. So, let us say pressure let us say I am plotting pressure with respect to time at any in a space medium. So, I will see that the pressure do not change. So, it is a steady. Now, in the same domain, if I try to see that there is some variation of pressure, then such a things we say unsteady. So, here in the nature of unsteadiness, your time axis is very important, because we need to see that at what times the, because at every instant of time the pressure values are different. The other classical stuffs that are of interest is laminar flow and turbulent flow. In general, laminar flows are orderly flow and turbulent flows are disordered nature of the flow. In fact, laminar flow follow a streamline pattern, whereas we do not see any streamline or pattern for a turbulent flows. So, when you say streamlines, these are the lines which are drawn in the flow feeds such that at any instant, if you draw a tangent at that point, it will give you the velocity vector. So, on the basis of streamlines in a certain volume, if you say, if you consider an array of streamlines and enclosed in a certain volume, we call this as a stream tube. More details of this analysis we will talk about in the subsequent lectures. Now, when the flow changes its states, that is, if the flow tries to attain from laminar to turbulent, or if it tries to attain from turbulent to laminar, that means how it can do. If you change the upstream and downstream conditions, the flow may change, this type of change can occur. In such cases, the flows that are treated as a, we call this as a transitional flow. Now, to decide whether the flow is laminar or turbulent, we define the term which is a non-dimensional term, which is a Reynolds number R e, and it is related to rho, velocity, v and L, that is the characteristics length, by mu, that is the fluid viscosity. That means, a single domain defines a non-dimensional number, Reynolds number, that says that under what conditions we can define the flow to be laminar or turbulence. This we have already seen in our classical fluid mechanics course. What is the role of Reynolds number in laminar and turbulent flow regimes? The other type of flows are of interest many times is a natural flow. Natural flow and force flow. Natural flow is normally buoyancy driven. For example, water boiling is a kind of a natural flow, and when some fluid, when the fluid is driven by some external agency, that means whenever there is a pressure difference mechanism which is being put, so that the flow can occur. So, such a flow we call this as a forced flow. Now, having said this, one can also think the dimensionality nature of a flow field. So, one can view the flow field phenomena occurring in a particular direction or not. So, traditionally orthogonal coordinates are the right approach in which decides the flow in a given directions. So, if they so in based on that we say whether the flow is one dimensional, two dimensional or three dimensional in nature. Now, having said this, the last part of this lecture, if you just summarize, that we have talked about inviscid flow and viscous flow, we have talked about internal and external flow, we have incompressible and compressible flow, we have laminar turbulent flow, steady unsteady flow, natural and forced flow, and one dimensional, two dimensional or three dimensional flow. Now, having said this, we can say that any type of combination is possible. So, one can have a viscous flow which is occurring in a pipe which is internal, and this viscous flow can be compressible or incompressible. So, any combination of and that flow may be steady in nature or unsteady nature. So, any combination of these things is possible. So, that is also left to the analysis in what framework we are going to do. And as far as our main fundamental things, as far as our concentration is fixed, that in this particular flow we will talk about or the fundamentals of compressible flow is mainly dealt with inviscid compressible flow, which is naturally occurring, and it is a laminar flow, and we will address them typically for a steady analysis in orthogonal coordinates, and in particular our focus will be in the 1 and or 2 dimensional framework. So, with this I conclude this lecture for today. Thank you.